Again, welcome to the videos on data converters. In this video, we shall see the continued successive approximation ADC, and then we will also see how does the flash type ADCs will work. This is the successive approximation ADC where we have a DAC based ADC. So this consists of a successive approximation register. The specialty of this register is, so this will actually give trial bits. So starting with MSB as 1, if the conditions are satisfied, we'll retain that MSB bit as 1 and we'll make the next lower MSB as 1. If that is not satisfied, we'll make it 0 and we'll make the next possible MSB bit as 1, and then that process will continue till n clock pulses irrespective of the number of irrespective of the amplitude of the input voltage. Now you can see, as we know that the conversion time here in case of successive approximation ADC irrespective of the input voltage purely depends on the number of bits we require from that ADC output. The entire conversion takes a total time of n clock cycles, and SA-ADC offers a major speed improvement over sequential search ADC. The sequential search ADC, we started from the bit 000 and then we keep on incrementing. Then whenever it comes close to that input voltage, we stop it and then say, okay, this is the digital equivalent of that analog voltage. If the full scale range voltage is applied, it will take 2 power n minus 1 as the number of clock pulses. Whereas in case of successive approximation, since we are giving a trials with starting with MSB bit as 1 and we are continuing that till only n clock pulses, we can able to complete the entire conversion process with only n clock cycles. Suppose if for instance a 12-bit SA-ADC with a clock frequency of 1 megahertz, this will complete the conversion within 12 microseconds, because we know that 1 megahertz corresponds to a clock period of 1 microsecond. Since it is 12-bit, it requires only 12 clock pulses or 12 clock periods, which happens to be 12 microseconds. So in this way, the successive approximation ADC conversion time is the least compared to the sequential search ADCs. Now this is a typical ACA based successive approximation ADC, where we have, so this AM2504 is a ACR register, successive approximation register, and this is a bipolar DAC here. So this voltage is fed to this comparator, where the comparator gives a signal to this SCR register, depending on the signal, is going to increment, or will going to retain the value of MSB bit as 1, or it will make the next MSB bit as 1, and that process continues. And of course, all these things will happen upon the upon giving a start signal. And after the conversion, after the n number of clock pulses, so in this case n is equal to 12. After 12 clock pulses, this EOC bit will be becoming high. So let us see what is this flash converters. As the name itself indicates, flash. So let us see how flashy the conversion is. The circuit uses a resistor string to create 2 power n minus 1 reference levels separated from each other by 1 LSB. So the major requirement of this flash converters is that we are using a resistor string to have 2 power n minus 1 reference levels. Assume that if the value of n is equal to 3, we will want to actually have 7 reference levels. So starting from 0, so there will be 7 reference levels, and each reference level will be separated by 1 LSB. So this is how it looks. So here we can see we have reference voltages. This is first one, second, third, fourth, likewise. So it is you keep getting the reference voltages. Each reference voltage is separated by 1 LSB. A bank of 2 power n minus 1 high speed latch comparator to simultaneously compare Vi against each level. Now you can see we have these are comparators 1, 2, 3, 4, 5, 6 up to 2 power n minus 1 is the comparators. Now these comparators are nothing but op amps. So where you can see one of the input for the comparator is taken from the input voltage. All the comparators are getting one of the input from the input voltage, and the other pin for the comparator is obtained from this network of these resistors. Now as soon as we apply the input voltage, when we actually give the start signal, so each of the output of the comparator will be either 0 or 1 depending on whether the input is more or the reference is more, whether the input is more or the reference more. Likewise, so we're going to get the output voltage instantaneously, meaning note that to position the analog voltage range properly, the top and bottom resistors are made, instead of making them 1R and 1R, so we have made the resistors at the bottom as 0.5R, this is 1.5R. As the comparators are strobed by the clock, once whose reference level voltage is, suppose if the reference level is below Vi, the output is logic 1. Suppose if the reference level is above Vi, then you'll get a 0. So as you can see here, whose reference levels are below Vi will get a output voltage of, because that depends on okay how you connected the voltage here. Suppose if the reference voltage is connected to V minus, and if the input voltage is connected to V plus, assuming that this is V plus, this is V minus, if this V minus is more than V plus, then we'll get 1 as the logic. Suppose if V plus is less than V in, so if V plus, this is V plus and this is V minus, if V plus is less than V negative, then we'll go to get 0. So here we'll be getting either 0 or 1 as the output of your comparator. The result, referred to as bar graph or also known as thermometer code, is then given to a desired output code of B1 to Bn by a suitable decoder such as priority encoder. So we shall just discuss this in detail in the next video. Now you can just see, supposing that we have 16 comparators. Out of 16 comparators, if the first two comparators are 1 1, and if all other comparators are assume that okay, 1 2 3 are 1 1 1 and all other bits are 0 0 0. So corresponding to this 16 digital input, we are going to get a corresponding decoder output. So corresponding to this decoder output, so we are going to have the analog input voltage will be represented by this binary value. Now for the given input voltage, since the input sampling and latching takes place during the first phase of the clock period, so as soon as we give the input voltage, once we say start, this sampling of the input voltage and it will be latched onto these comparators in the first half of the clock cycle. Decoding will be done during the second phase of the clock cycle. That is, now you can see everything is happening in a single cycle. The entire conversion takes place in only one cycle. So this ADC is the fastest possible ADCs available, because within in a single clock we can able to get the output voltage. Now flash converters, it is used in high speed applications such as video, radar signal processing, where the conversion rate on the is of the order of millions of samples per second, because when we are actually tracing any enemy targets, the radar signals will be has to be processed very fast. Now since the processing time is very small, so we're going to use this flash converters. Millions of samples per second will be processed, whereas SA ADCs are generally not fast enough, because now in the previous slide we might have seen that the SA ADCs will take n clock pulses, whereas in case of flash converters, flash ADCs, it will take only one clock pulse to complete the entire conversion. So what are the other facts about the flash ADCs? The high speed inherent sampling advantage of flash ADCs are the offset by 2 power n minus 1 comparators are required. Now you can see for a 3-bit ADC we are supposed to have 8 comparators. Assume that you have a 8-bit converter. 8-bit comparator requires 255 comparators. Just think of having n is equal to 10. So you are supposed to have 1023 comparators. Suppose the value of n is more than 10. So you can just think of the number of comparators required to process the data within single clock pulse. So these high-speed flash ADCs are having the major disadvantages of having large number of converters. So it requires 2 power n minus 1 comparators for getting the output voltage in a single clock pulse. So flash ADCs are available in CMOS technology with resolutions of 6, 8 and 10 bit. Sampling rates are ranging from 10 to hundreds of millions of samples per second. Depending on the resolution, power dissipation rating is in the order of 1 watt or less. You can see the amount of power dissipated is very large because we are having so many number of comparators, because all the comparators will consume energy when they want to operate for a proper conversion from analog to digital waveform. So the take home from this flash ADCs is that, so as we can see in the circuit diagram or the block diagram, we have 2 power n minus 1 comparators. So each comparator is getting a voltage from the input voltage as well as from these reference voltages. So we're going to have 2 power n minus 1 reference levels also, so which have been separated by 1 LSB. So once we get some coded value here, so that coded value has to be decoded. Assume that you are having a 3-bit DAC. If you are having a 3-bit DAC, we'll be getting actually 8 combinations of the input voltage. So we need to have a decoder like structure here, system. So this, assume that you have this as 1 and all others are 0. Assume that okay, you have the first 4 bits as 0 0 1 1 1 and other bits are 0. So you are supposed to make the output voltage as 1 0 0 for a binary equivalent or digital equivalent of that. So in the next video we shall take 2 to 3 examples of flash converters and try to understand the exact decoder design and how does these flash converters will going to convert the voltage depending on the input voltage. We shall also see how does a decoder has to be designed so as to get a proper digital equivalent of the input signal.